the invention blogs of Ollie the inventor. The really bad singing voice at the moment. The really bad singing voice at the moment for you. Okay, so let's go wave time. Okay, so when it comes to light waves, I think, now here's the thing, I think scientists actually have a problem in the way they see light waves. So here's two light waves. Look at them, they're both sine waves. And what do good scientists do? They break everything into sine waves. And that's how, using the Fourier transform or just using a prism. And the problem with that is you're losing the phase relationship between the things. You're losing the shape of the waves. So this here is a triangle wave. Whoops, a dizzy. Triangle wave. I keep on screwing up on that one. So a triangle wave. Scientists say they don't know what pink is. Pink could be a triangle wave, a curved wave, whatever. That's a triangle wave, okay? So when they send it through their prism, creating their discount Fourier transform, they forget to measure when with the brightness. So that's one of my inventions, is after it gets sent through a prism, the light from an element as electricity is passed through it, you need to send it through a time of flight measurer. So something that scans it, a mirror, a spinning mirror that scans the actual light across and creates a sort of a dot, dot, dot pattern. So after it's sent through the prism, you send it to a spinning mirror. So spinning mirror, I'll draw it in blue, spinning mirror. And then that pattern down there gets shot onto a wall and creates a sort of a brightness, not a dot, dot, dash pattern, more of a brightness wave. So after your lines are created from sending your light from an element through what are these things called again? Prism. A prism. That was me being really stupid there. You send it onto a spinning mirror, and a spinning mirror. Actually, I'll draw the other lines. Sorry. The spinning mirror scans it across the wall and creates a brightness and darkness pattern. With that, you can recreate the shape of the wave coming off the element. So there you go. That's one of the things you got to use you can do it with X-rays as well, and I'll probably be able to tell you a lot of the chemistry of what you're dealing with. So that would help in chemical continuum theory. It'd just make it a sort of a drawn wave rather than everything being made of sine waves, which is the way scientists deal with all waves, is they just treat them as a list of sine waves at different integrals, which is essentially just a really, really big simultaneous equation. And you're just turning the entire thing, the entire function into just a giant simultaneous equation, which robs it of the actual shape of the wave. There's another wave that I talked about in the last video, which is the Tesla coil tall wave. So if you were to put like direct voltage through the coil in the Tesla coil, you'd start having, say, I'll use blue as the middle line. I'll get a new page. So say blue is the middle line between minus and plus voltages, right? And what you start to get is this. Or you start to get a DC wave. So the electricity is all the way up there, and then the wave is starting to happen there. Okay, so the electrons hitting a metal surface that's been charged, giving off electrons. Why does that happen? Now, there's several theories I've actually put together for this to work. So theory number one is what I call the inductor capacitor theory. If you have a bunch of lines side by side, so you have your wave, right? And all those blue lines are wires side by side. And when one oscillates, it sends the wave down to the next one, the next one. Now, that wave shape is wrong, and I'll go into that later. But for now, it's just for simplification purposes. What happens in an electronic circuit is that wave travels more through the induction side of the actual electric circuit than it does through the capacitance side when it's long. When the wave is short, it starts moving as a capacitance wave. And that's probably why X-rays, you mightn't actually be able to orient X-rays the way you can orient, polarize X-rays. Might be harder to polarize X-rays than it is other ways because they're traveling more as capacitance waves than they are as induction waves. So that's theory number one. Put a line under that. Theory number two is what I call the spin kick theory. So as your wave hits the piece of metal and the electrons get kicked off. The electric charge gets kicked off. I don't believe in electrons. What's happening is it's acting as an induction motor, and it's creating spin, and it's spinning so much that it kicks itself out of the material. So that's another theory of why I think that might work. And the third theory is that electric charge that travels, I'll do it in green this time. It can be either plus or minus. Electric charge. So an electric wave is a neutral wave, right? Like a radio wave or a light wave. It doesn't have a charge. Whereas these are electric charge, what we call electrons, are actually charged waves. So they're waves that have been sent into, like the tall Tesla waves I said earlier. They're waves, where did I have it? The tall Tesla waves. Like those tall Tesla waves, they're actually just charged waves. So they're the three theories I had on electric charge, the way it works that way when it jumps out of material. There's another thing that I want to talk about. I'll just put this over here, which is what I call a zero vector. So with my zero idea, the idea of having sized zeros, you can do a thing called a zero vector. So if you have I call them compression and tension vectors. So if you have that vector, right, that sums to zero. But say if that was 100, it would sum to 100 0. If it was 1,000, it would sum to 1,000 0. So 0, 1,000, or so that would be the compression force that that vector creates, or the tension. So if you have a conductor that's a ball and you've charge on the inside, so if you have a ball, it won't move in any direction. Like if it's closer to that wall, it won't move in, but it'll still be compressed. And that's the thing that works with the electronic circuits they use with heated coils. What are they called? Vacuum diodes and vacuum triodes. That's the reason why those work, is because of that compression vector. It's compression vectors facing in all directions with that. If you had a minus one of those compression vectors, it'd be a tensile vector. So you'd have a minus and positive 0, and it would point out and in. So that'd be the zero effect. So if you're looking for zero numbers on the number line, so 0, 100, 0, 100 would be like that on the number line. It'd be between those 2 points. It'd be a kind of a balanced number. So you can do the same with a one-dimensional number line, is to turn the one-dimensional number line into a vector, and it works like that. What else are we looking at? The other thing is it would shrink and compress the charge inside it. So it would make the electrons smaller or bigger, allowing you to see more accurately or see smaller amounts or smaller, what are they called? My dinner's on my jacket. It would allow you to see smaller objects by using that container and charging the outside walls positive or minus depending on what you want inside it. What else have we got? So the other thing is types of waves. So this is so I've discovered that there's more than the 2 types of waves we normally talk about. So the 2 types of waves we normally talk about are the transverse wave and the longitudinal wave. So longitudinal and transverse wave are the 2 we normally talk about. So they're the normal 2 we normally talk about. Okay, there's another one called a torsion wave. So you imagine a cylinder and it goes like that. So I'll draw a torsional wave. Torsional wave. Okay, so that's a torsional wave. See, the cylinder is rotating, and then the rotation oscillates back and forth. That's called a torsional wave. Now, that torsional wave is interesting because it doesn't just have to be tangential to the movement. It could be in and out. It could be towards the movement and out of the movement, depending on the amount of dimensions you have. If you were to take a ball, so if you take a ball in 3-dimensional space and that dot is a point on the ball and it has a direction up, if you were to rotate in any shape that you could create, like it doesn't have to just be up and down, it's just a shaped rotation, that then could be sent down the line, and that could be the torsion wave. So that's the 3rd type of wave, is a torsion wave. The next one is a compression wave, longitudinal compression waves. So when you shine two lights at a material that are slightly out of phase, they create black spots or bland black spots. And at those spots, they create what I call compression waves. So if you were to look at the longitudinal wave like that, so I'll circle it in a big circle. It looks kind of funny. But see, the waves are coming in the opposite direction. And when they mix with each other, they create what I call a compression wave. So at that point, the wave is going both up and down at the same time. So it's compressing. So if you shine those lights and it creates those lines on the wall, the lines are being turned to heat. So that was one of my ideas for a heat beam, was to use a semi-silvered mirror and mix 2 laser lights together that were out of phase to create a compression heat wave. And that heat wave then would be absorbed by everything that's absorbable, even mirrors and things like that. So it was a method of creating a heat wave. Black is interesting. I'm not sure about black, but I like to think it's a circle wave, or a wave that that basically, it's kind of a it ends up as infrared. So, and different black objects. So I like to think it's more like a circle wave. So if you had a shaped wave, and you had if you just cut out a circle in half. So if you had a circle and a circle there, and you just went like that, and that's the shaped wave. So the last wave I'm going to talk about is the how would you describe this? That wave. So light waves are not shaped like that. They're shaped like this. I'll do it in red actually, because no, I'll do it in blue. I'm just going to double underline it for you. So light waves are shaped like this. I like to call it a mirror wave or a minus wave. One of my friends in school talked about, the way there's base 2 numbers and base 1 numbers, he talked about base minus numbers. So I always thought that every other thing changed the base. So if it was 1, it was 1. Then the next carry became minus, and then the next carry became positive, and the next carry became minus. So you see, if you get a what's it called? An what are they called? A transformer. Pretend these are wires going up and down each of these arrows. If you send electricity down the wire, the reaction you get is up the wire, and then the next one would react down the wire. So you're actually not, when you're sending off an EM wave, you're not sending off this pearly, beautiful wave like that. You're sending up like a very, very fine sawtooth wave, because they're all traveling in the opposite direction to each other. The lines, it's like it goes up, down, up, down. It's like what's it called? A tooth wave is the way to describe it. A tooth gap wave. So you imagine that everything that goes up goes. So when that accelerates downwards, that one will be accelerating upwards. That one will be accelerating downwards, and that's how it works in transformers, and that's how it works in waves. And that's one of the reasons I think the electron, or the charged, you call them electrons, kick off metal, is because of that also. Because the higher frequency of that maybe turns it into something like that, or something similar like that. So that is what I call a box wave, or I'm not sure how I described the wave, but it's basically means that every thing beside it. So if you push down, instead of the wave pushing bit beside it pushing down, it pushes up. So a sort of a shear wave, that's the best way to describe it. A reverse shear wave. So you push downwards, that one will push up. So it's kind of like a C wave. As you push down on the C, the bit beside it pushes up, and that's how electric light works. And it's kind of how the C works as well. So that's all of them, I think. Yeah, that's pretty much as she goes. I'm going to make a note about statistics in using statistics in science. When you make your model, do not add noise to your model. Okay? When you're in science, they usually add the normal to it, the normal noise, the distribution to the actual scientific model. The problem with doing that is you're already dealing with an environment with noise, and then you add noise to the model. By doing that, you're making your things hilariously inaccurate. Second of all, don't quote percentages as accuracy, okay? Just get rid of that. Just say closeness to model, and simple as that. What else we got? Give me a few seconds. I had another thing I wanted to talk about. X-rays, light waves, charged waves. If you give me a few minutes, it'll come to me. So just muddle around in the background and I'll come up with something. If you want to make accurate electron microscopes, connect them into a create a really, really long, thin magnetic field, sort of like an MRI. And then the electrons will be forced to follow straight lines. So it's kind of like an electron stamp. What else? Another way to test chemical continuum theory was if you keep folding an insulator and a metal, they should continue on acting as an insulator. So, like if you folded it so it had a billion or a trillion layers, it'd have to be very similar materials. Only insulation is different, and folded it so it had a billion or a trillion layers. The insulation should stay the same between the materials. The capacitance won't. The capacitance will probably go down, but you'll have to just wait for it to charge up and then test its resistance after a certain amount of time. What else? Something about waves that I can't remember. That was it. So there's another type of wave, which is, and we use them for, is polarization wave. Okay, so as light travels through the thing, it can have polarization, so it can have an angle like that. And we use circularly polarized light to make like things that will only go through one eyepiece or another for 3D films and things like that. But you can actually wave the polarization, and you can coil it, and you can turn it, and you can. There's two other things, is that it might have a spread. So it might be that all polarization is just thin, and all the polarization. So you'd have to measure the time of flight polarization. So it might be that polarization is just very, very thin, or it might be very, very spread out like that. So there, one side is positive and one side is negative. Say the top side of that is positive and the top side of that is negative. So there might be spread polarization. So that's everything. That's all my thoughts on waves. If you wanted, one of my ideas for STEM matter was to get the waves being created off of the materials, and then feed it back as an EM wave into STEM matter, and the STEM matter would sort of congeal into the matter. But that's just theoretical. It mightn't work. You could also 3D print with it, maybe, if it worked that way. Or you can maybe create pocket dimension space waves, or sections of pocket dimensions, which is like a fourth dimension, or a dimension with an insulator dimension, so insulator space. So that might be why we can't get into fourth dimension space, because there's such a thing as insulator space. So I think that's all I have to say on my inventions for waves. So thanks for watching, and yeah, thanks for watching, and have an enjoyable evening.